Okay, so we're going to start with kind of talk about this this problem that I created, a crazy straw. And I think I said this was 25 degrees, I think. And
No,
this
that
is
one
30.
That one 30.
Okay. Right. So obviously this is pretty sloppily drawn, but you get the idea.
Yeah.
Okay, and then we've got this right here. We've got an opening here. We've got an opening here. And if I wanted to, actually not as bad as I imagined my drawing would be. Okay, so what I said is, okay, this is 6 centimeters, 6 centimeters,
Yeah.
0.06 meters. This is 0.02 meters. Okay, so, all right, so the key here always is if you're doing a momentum problem, so the equation looks like what? Sum of the forces plus rho VQ.
Or be killed in.
Rho VQ out, right?
Yeah.
And we know we've got, like, this is the in and this is the out. So in other words, we need to know Q, which I gave you, so that's no problem.
But we
need to know V for both of these. Yeah. That's pretty easy, right? Because and we need to know the angles, but we got the angles. But we need to know the V and that's pretty easy because we got V equals Q over A. Right, so that's good. We didn't know the density, and I said this is soda with a specific gravity of 1.0. So that's pretty cool, right? So we're pretty good on this. Like, this is not the hard part of this one.
So,
okay? Other than remembering that we have to account for these angles. But the hard part is the forces. So, all right. So, and what I really wanted you guys to do is I wanted you to think about this. So the reason the water is flowing from this point, which if you want, we can call 1. We can call this point 2. Is the expectation really would be that the flow would go from 2 to 1, right? Because that's the way gravity goes, right? But it's going from 1 to 2. So why is it doing that? I'll give you a hint. It wouldn't be doing that if you didn't have if you weren't sucking on it.
Yeah, because that the force drain the water from the cup to your mouth.
Right. So what you're doing in your mouth is you're lowering the pressure. Right. So the pressure at 2 is much lower than the pressure at 1. Right. That's why it's going from 1 to 2. Ultimately, really, there's atmospheric pressure right here. Okay. And it's essentially driving this all the way up around this thing until it gets to P2. Okay. So, all right. So let's get our forces. Okay. So you've got your lips. So I'm going to call this the force anchor, or really this is force of the lips of the X. Force lips X. And then you got the force of the lips into Y.
And then you got weight your straw and you got weight your soda.
Right. You got the weight of the water. And you got the weight of the soda, right?
Yeah.
Okay. And then we have to think about these pressures. And so we've got, and they may not really matter all that much, but the point of the problem was to get you thinking and to make sure that you get all this. But there is a pressure right here.
Yeah, which is P1.
P1 times A1. So that's a force. Now that's got an angle on it, right? So it's got an X component and a Y component. And then we've got a pressure here. And this one's like P2A2. And then that's pretty much it. Well, no, that's not exactly it. So the last thing here, and I said it in words. I don't have it. Let's see if I can get it on my computer screen. Let me shrink this right here. Oh, I don't have it open, but somewhere in there I said something about assume that the pressures on all sides kind of cancel each other out. So basically, when you start working with
another test too.
Yeah, something happened. My recording stopped recording. All right, so so I guess we're starting again. All right, so I'm picking a problem off of old homework. So if you got your computer and you wanted to follow along and see the problem, this is from homework 12. I don't know where this problem came from originally. I'm assuming that if I were to type this into the internet, it would pop up, which means on Chegg or something. So I'm assuming This one has been, basically it's been ruined. It really stinks because people use Chegg. It means I find these perfect problems that would be very good for teaching people, but I can't use them because they've already been ruined. So I have to make up my own, and then I screw my problem up, or it's too hard or whatever. And it's just really ruinous. Okay, so an amusement park has a water slide as shown below. Consisting of a smooth curving channel down which visitors slide. Okay, so water at 10 degrees C is pumped to the top. Okay, so here we go. We've got a water slide. Oh, give me a pen here. Water slide. Okay, now it's got a whole bunch of, scaffolding or whatever to hold it up. Okay, so it is pumped to the top of the slide through a 4-inch diameter pipe. Okay, so we've got this little pipe that's kind of coming up here. Okay, and it's pumping up 60 feet to the bottom of the pipe. Okay, 60 feet. And so this is a 4-inch diameter pipe. 4 inches. This is given. And the inlet to the pump is a 6-inch diameter pump. Okay, so down here somewhere we've got a pump. Let's see. Okay, so this is going down 60 feet to, let's see. I wish I were a better drawer. Okay, this is the bottom of the water slide. Or I guess the structure that holds the water slide anyway. Okay, so this is like scaffolding or, whatever this stuff looks like. It's holding the water slide up. Okay, so the pump, so this 4-inch pipe comes down to here. And then there's a 6-inch pipe that comes out like this. Okay, because at the bottom of this water slide, there's a reservoir here. There's water in there. Actually, there isn't water there. Okay, the water is actually 1 foot below. They had to be weird about this, didn't they? Okay, so somewhere over here is the edge of this reservoir. And let's see. Son of a. Okay, I'm really struggling right now.
Maybe we don't need to do it.
No. It's a great problem is the thing. It's just what they're trying to do when they create these problems is they're trying to get you to think about a lot of the different things that are going on. It's every problem, like they put in what a lot of students would call tricks, but the point of the tricks is to make you think, so that when the test comes up, you're not like, well, wait a second, I never saw this before, so this is 4 inches. This pipe is 6 inches. Yeah, that's pretty much it. We don't have a length of that one, do we? Okay, and then yeah. Oh, and then between, and this is 4 feet. Okay, so this little black line right here, this black line is just, that's nothing. Okay, that's just there because it's just there to show you that all this stuff is the same level. Okay, so let's see. Oh, this is a 6-inch pipe. Okay, and then it says the friction losses. So the loss due to friction, head loss due to friction, and the head loss due to friction. We got 2 head losses. Okay, and this is going to be HF4, so that's in the 4-inch pipe, and HF6, that's in the 6-inch pipe. So in the 4-inch pipe, it's 0.7 V4 squared on 2G. And in the 4-inch pipe, in the 6-inch pipe, it's 0.3 V6 squared over 2G. Okay, so those little subscripts 4 and 6 mean the velocity in those pipes. If the flow is to be a constant, 1.0 cubic feet per second, okay, and the pump, the efficiency of the pump is 65% efficient. Okay, determine the power that should be supplied to the pump. Okay, so we want to know required power. I always write it as 2 pump. There's probably a better way to write this, but that's the way I do it. Okay, this is a lot. This is an awful lot of information. This is like a huge jump up in difficulty. Well, not necessarily, but it is a jump up. So let's we're going to take this like little by little, and this will probably be, maybe it won't be the rest of everything, but we'll see. Hold on, I want to enlarge this so I can see what I'm doing. I want to see what you guys see. Okay, so okay, let's see. So what we're looking for here is really, this is almost like a mechanical engineer's problem, because we're looking at a pump here and we're thinking about what's going on with the pump. So I'm going to work this backwards. Okay. And so basically, if I think about the pump, and I'm going to draw this and then erase it, but I got to lay a little pump right here. Okay. And what's happening is I need the pump to spit out a certain amount of work, right? Or power, I guess, or energy per time. So power. So a certain amount of power is coming out of this sucker. And in order for it to do that, I have to give it a certain amount of power, right? I have to plug it in. Okay, now it so happens, because of the law of conservation of energy, I'm never going to get out as much as I put in, right? I'm going to lose power. That's just the way it is. So I never remember what this equation is. So I always just think about it like this, just kind of doing it on my own on the side. So let's see. So this efficiency says that this pump is 65% efficient. That means I'm going to put in a certain amount of power here. I'm going to put in, like, I don't know, a good bit of power. I'm going to put in whatever I put in here, but I'm only going to get 65% of that out, right? Because that's law of conservation of energy. Some of it's going to be lost to, friction, or generally friction, some sort of friction or rubbing or whatever going on in the pump. Okay. Or, turbulence in the water, whatever it may be. So that means that, let's see here. So this A to P, that means that the power that's going in is 65% of what's coming out is 65% of what goes in. Okay. Does that make sense? Okay. Make sure that you can kind of internalize that. So this is 0.65. This is basically 100%, and this is 65% of that. Okay. So there you go. So what we're looking for here is we're ultimately looking for what goes into the pump. So this is what we're looking for. We already know this. So we need to figure out a way to get this work out. Okay. Or this power out, work per time out. Okay. So this is what we're looking for. So I'm just working backwards here. Okay. So now the W dot out. Okay. Now all of that that's going out, that's going to the water. Okay. That's being used to supply energy to the water. And so there's an equation for that. Okay. So this is, and that's the power that's going to the water, is gamma HP Q. Okay. So again, we're just kind of working backwards, and we're thinking about what we have and what we need. Okay, gamma, well, this is water. We're good to go. HP, well, we don't know what that is. Okay, Q is given. Okay, so we need to figure out HP. Okay, and that's this whole problem, really. So let's figure out HP, and then we've just got these extra equations once we get HP. Once we get HP, we plug it in here, and then we take that value and we plug it in here. Okay, so how do we get HP? So we get HP, because now I'm actually going to start working this problem, is the energy equation. Energy.
Add the head loss plus.
Right. So it looks like this. Plus HP equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT plus H L, or H, the head law, H capital L. Okay, each textbook calls it something a little bit different. Okay, so now instead of thinking about this as just head, we need to start thinking about this as energy. Okay, because now we're going to I'm going to erase all this so we have this space. Okay, we'll come back to it. It's fine. Okay, it's just to kind of give you an idea of where we're going and why we're doing what we're doing. Okay, and what we're aiming for here is this is the ultimate goal right here. Okay, now real quick, I'm going to do a few things. that are just going to make this simpler, because we want to think about this exactly the same way we think about Bernoulli, but these are energy instead. Okay, and that's why we've got this little alpha here, which I explain in the what do you call it, in in the lecture. So I forget what it's called, the turbulent correction factor or whatever. So what we're going to do for this problem, well, I don't know what we're going to do for this problem. So what I want to do is I want to pick an easy point to start with. Okay. Oh, there's a lost dog out across the street, and it is just leaving. Okay. I would go get it, in fact. All right. So we want to pick an easy point. Now this one's interesting because what's happening is the water is here and it's flowing all the way down here. It's hitting this pump and then it's going up here and then it's sliding all the way down this slide, right back into here. So it's a circular system. So it's kind of like, well, where could 1 be and where could 2 be, et cetera, et cetera, et cetera. Like it could be, and the key here is you just want to pick a place where it's easy, right? We want easy places. And so what I'm gonna do is I'm like all along the slide, I don't know anything about its velocity. I don't know anything really. So I really don't want to pick, like if I picked right here, I would have no ability really to work with the velocity, right? So, but what I can do is I can pick right here as a point. It's gonna be my point 1. Okay, because that's an easy point. I know its velocity is 0, right? Because it's the head of a tank. I know its pressure is 0. Like we like tops of things, right? And we know its elevation. We just have to pick a datum. The other place that I like to pick is I like to pick this spot right here. Okay, because it's exiting into the atmosphere. So I know the pressure there is 0. I know its elevation and its velocity I can get because it's exiting that pipe and it's a 4-inch pipe. Okay, so let's go ahead and let's get those velocities right now, right off the bat. We're going to call this V4, so velocity in the 4-inch pipe. I'm going to go ahead and get velocity in the 6-inch pipe, just because I'm doing this right now. So it's going to be Q over A. Q over A. So the Q is 1 CFS. The area is pi. What are we at? 4-inch pipe. D squared on 4. Pi on 4 times D squared. So it's that's 1/3 of a foot squared. And this one's going to be 1 CFS divided by pi on 4. And this is a 6. That's a 1/2 foot squared. Equals. Okay. Let's get out our trusty dusty calculator. And we'll say pi divided by 4 divided by 9 to the negative first power. This is 11.495. 11.495 feet per second. And then we've got, let's see, pi divided by 4 divided by 4 again to the negative 1 equals 5.0930. 0930 feet per second. Okay, so that's a little feet per second kind of squeezed in there. Okay, so now we got velocities. We only really need one of them for the energy equation, but things are going to get a little bit more complicated. All right, so let's start analyzing our points. Oh, this is point 2. This is point 1. Okay, so let's start analyzing our points. Okay, V1. Okay, pressure is 0. Okay, because it's atmospheric. Okay, the Z1. Well, we have to pick a Z that makes sense to us. It could be anything we want. I think it's kind of up to you, like where do you want the datum to be? On this problem, you know, usually I like my datum to be kind of like the lowest point. But in this problem, because I guess things are a little weird on this problem, right? So I'm not actually going to make my lowest point. I'm going to make the water surface because everything kind of comes off of there. So I'm going to make that my datum.
So Z1 with negative 4?
No, Z1, because this is my datum, then Z1 is on my datum.
Oh, 0.
So Z1 is 0. Okay, so this is my datum.
60 feet.
And then Z2 is going to be 1 right here plus the other 60. So it'll be 61.
61.
Right. So V1 is 0 because it's the tank or the Lake Tahoe assumption or whatever we want to call it. Okay. And then let's go to P2. We're going to skip this because this is what we're looking for. And then P2. Well, the pressure 2, it's atmospheric because it's open to the atmosphere there. Z2 is 61 feet. And then this alpha. So this alpha is a turbulent correction factor. So I'm assuming you guys haven't watched the videos yet. Maybe you have, maybe you haven't. But I'll go ahead and we'll just go ahead and do it real quick. So basically what we're doing is we're checking to see whether or not this is turbulent or not. It's almost always turbulent. That's the hint. So if you're stuck for time, just go assume turbulent. And so alpha equals 1. That's what I would do if I was stuck for time. Okay, right now we have plenty of time, so we're going to go ahead and test it. Okay, so we have plenty of time, so we're not going to do that. We'll go ahead and test it. And we'll say, well, the Reynolds number equals the velocity times diameter of the pipe divided by nu. Okay, the Reynolds number is the velocity of the pipe, which is, let's see, it's exiting the 4-inch pipe. So that's 11 feet per second times the diameter of the pipe, which is 4 inches. So that's 1/3 of a foot, divided by the viscosity of water, which I think is 10 to the minus 5 or 6. I can't remember. Give me 1 second. I'm going to look this up because might as well get this right. Viscosity of water. Oh. Notice also there's an error on this problem. Well, if you look up this problem, it says it's at 10 degrees Celsius, which is ridiculous because the whole problem is in British units. Basically to me, I just take that like, okay, it's not a crazy temperature. It's like not outside the normal range. And you might say, well, what does that even mean? I mean, like, it's kind of something that we might see in nature. So to me, what that means, let's see, degrees F. So somebody's got something going on. Let's see, 10 to the minus 5, it looks like. Yeah, so at like 70 degrees-ish, it's 10 to the minus 5. Okay, 50 degrees, it's 1.4 times 10 to the 5th. Now, here's the thing, okay, and I think this is important. It never really comes up, but well, it does come up because people look at my keys and they get very upset. Is what happens here is that a lot of people will spend a lot of energy looking up this number right here, okay, and I just looked it up very briefly, and basically, if you look it up between like, I don't know, 40 degrees F and 90 or 100 degrees F. Basically, this goes from 1 to 2 times 10 to the 5th. Okay, that difference doesn't really matter. Okay, because all we're trying to do when we do our Reynolds number is we're just getting an order of magnitude. Okay, so I'm going to show you, like, when we calculate this, that it doesn't really matter. I'm just going to leave it as 10 to the minus 5. Plug that into my calculator, and I've got 11.495 divided by 3 divided by 10 to the minus 5, and we get some really massive number. So 3.8 times 10 to the, let's see, 1, 2, 3, 4. Okay, 10 to the 5th. Okay, that's my Reynolds number. Okay, in order to figure out whether or not this is laminar or turbulent, the transition in a pipe is somewhere around 2,000 to 4,000. Okay, so we are, so 2,000 is 2 times 10 to the 3rd. Right, so we are 2 orders of magnitude larger than that. Okay, so whether or not we have a 1, sorry, I just accidentally minimized. So whether or not we have a, let me make sure I'm still recording. Yeah, okay. So whether or not I've got a 1 or a 2 right here, doesn't matter. Okay, so don't worry about it. Okay, and in fact, when I plug this velocity in right here, when you're working these problems, don't be as exact as I was just now. I know I say always use 5 significant digits, but on your Reynolds number calculation, you can just go like, you could just go to 1 significant digit and go 10. Okay, it's not going to matter. right? When I like, even just by looking at this, you can go, okay, well, 10 divided by 3, I'm about 3 divided by 10 to the negative fifth. Well, I'm going to be at about 3 to 10 to the fifth. Way big enough. Turbulent. Alpha equals 1.0. Move on with your life. Okay. So in this case, don't sweat the significant digits on your Reynolds number calculation. Okay. Be as quick and easy, as dirty as possible. It's hand wavy. In this class, it'll almost always be turbulent unless I intentionally try to make it not turbulent, just to make you check it and get 2.0 instead of 1.0. Okay. And so, basically in life, unless you go work in really small systems, like really, really small systems, like unless this is really, really tiny, so like if you're like a geologist and you're working on like water flowing through the ground, okay, if you do groundwater, then you might get laminar flow. Okay, anyway, so this number right here, this alpha, we're going to assume is 1.0. So that means over here, basically I can ignore it because I'm multiplying by 1. Okay, I know V2 squared over 2G. I'll go ahead and plug that in. And then this HT right here, this is for a turbine. There's no turbine between 1 and 2, so we don't worry about that one. Okay, and then this head loss, it splits out into 2 forms of head loss. So there's one due to friction, and there's one due to what we call the minor losses. Okay, so there's like one due to minor losses and one due to friction. I haven't taught you how to deal with the minor losses yet. Basically, there's a bunch of losses due to like this entrance or like to this bend in this pipe. There's energy that just gets lost anytime the pipe changes or something goes weird with the flow. We're not going to worry about that right now because we haven't done that yet. So we're not going to worry about that yet. It's not that it doesn't exist. It's just that we haven't learned it. And then we're going to deal with this HF. And this HF is basically all the things that cause us to lose energy. So it's going to be HF4 plus HF6. So basically we're going to lose energy along the walls of the pipe in the 6-inch pipe and the 4-inch pipe. Okay. And this right here, this is a simplification that we will very quickly make more difficult. Okay. So, enjoy it while you got it. Okay. So ultimately this looks like this. I'm going to kind of draw it conceptually here. HP equals Z. No, come on. Don't give me that. Z2 plus HF4 plus HF6. This is very important to me that you understand what is going on here, that this will make sense to you. So basically what happens is the pump, which is rated in head. So basically the number that goes into this pump, that's how high the water can raise. That's how high it can raise the water in an ideal circumstance. So if I say, we've got 100 foot, this pump delivers 100 feet of head. That means if there's no friction, it can raise water 100 feet. Okay. Or like in a case where there's no velocity, it can maintain a head above it of 100 feet. So it can maintain 100 feet of water above it. Okay. In this case, right, how much, whatever we put in here, 61 of those feet are going to have to go here. And then some more feet are going to have to go to overcoming friction. Right. So it's this like nice kind of balance. Now, how much? Well, we actually have to calculate how much right here and right here, right? We have to calculate those things. So usually I would put those in one long equation down here. I'll put a really long equation down here to solve that. I'm going to do it on the side because I like to have, I want to be able to think about how much is going to each term of friction. Okay. So I'm going to do it as an aside up here. Just going to make myself some space. I'm going to keep V4 and V6. All right, so let's see what we get. So we're just going to plug these in up here. HF4, that's the larger number. So 0.7 times 11.495 feet per second squared divided by 2, and the gravity is 32.2 feet per second squared. And then this one's 0.3 times 5.090. Dadgummit, I forgot this term. Okay, let's add that one on. plus V2 squared over 2G. Okay, 5.0930 feet per second squared divided by 2 times 32.2 feet per second squared. Okay. 11.495, that's the V4. Oh yeah, okay, so this V2, by the way, before we get too far removed, this V2 right here, that's the velocity at 2, so that's the velocity in the 4-inch pipe. Okay, so that's the number I just erased. This is 11.495. Okay, so just, be aware of that. By the way, this is my most common error, is going from this line to this line and forgetting terms. I do it all the time. So hopefully not on any of my keys. And then I guess up here, I'll go ahead and get V2 squared over 2G. V2 squared on 2G, which is just this right here, right? So I don't need to do that twice. Okay, so 11.495 squared divided by 64.4 times 0.7 equals 1.4363. And that has units of feet, which is awfully nice. All right, and then the one below it, 5.0930 squared divided by 64.4 times 0.3 equals 0.12083. 12083 feet. All right. And I guess I forgot on that first one. Take this 1.4 and let's divide it by 0.7. Okay, so this one is 2.0518 feet. All right. So in this particular problem, this pump is raising the water this much, but it also has to overcome some friction. So 2 feet of friction from this guy. HF6 looks like 0.12083 feet, and then 1.4363 feet. Okay, so the pump in this case, it's just going a little bit more than 61. It's not going a ton higher. Let's see, 61 plus 1.4363 plus 0.12083 plus 2.0518. Okay, so we get 64.609 feet. Okay. So basically the pump is taking water that really has no energy at all, and it's giving it a little bit of velocity, a lot of elevation, and overcoming some friction. And that's where the energy goes. And to me, it's always helpful to think about this in terms of energy, to stop and step back and look at your problem and think about what's going on. Okay, so that's it. And then so then we just need to solve for the whole thing we came for, which is okay. So that's cool. Well, now how much energy? So that pump is giving the water that much head. So how much energy does that equate to? Okay, or how much energy per second, really? So the power of the pump, okay, pump to water, okay, equals gamma HP Q. One day I'm going to derive that. I've never actually spent the time. W dot, let's call it pump or whatever, but W dot to water doesn't matter. So the gamma of water, this is 62.4 PCF. Okay, the HP is this number. Of course, I did this with no room. And the Q is 1.0 CFS. Okay, so the W dot pump equals whatever that number is, 62.4 times 64.609. Okay, and this number is often large, 4,031.6. It's good to check units at this point. Pounds per cubic foot cancels with the cubic foot here. So I've got pounds times feet, and there's a seconds on the bottom here. So pounds foot per second. So usually this is written as a foot pound per second. Okay, noting a foot pound is a unit of torque or a unit of work, and a second is a unit of time. So this is work per time. Okay, so that's power. So sometimes we write it like this, sometimes because people are, well, we'll just leave it like that for now because we're not done. So we need to know, well, if that's the case, how much do I need to supply to the pump? Okay, so this is from pump to the pump. Well, let's see, this is 65% of what I'm getting out or what I have to supply the pump. So basically I need to divide this by 0.65. If you can't see that, we can you can just think about it as like, okay, well, the water, let's see, to pump, I keep calling this something different, versus W dot to water. Okay, and what goes to the pump, well, let's see, that's 0.65, 0.65 times what I give to the pump is going to go to the water. Sorry, 65% is 65% efficient. So if I have this number right here is from pump, we could also call this to water. All right, so this number goes here, 40, 31.6. So in order to get this to pump, I need to take that number and divide by 0.65. Sorry, is that making sense? I know I'm I know I'm jabbering. Max, you kind of look like you're okay. Paul, you okay with that? Yeah, okay. All right, so we divide that by 0.65 and we get whatever we get. Divided by 0.65 equals 6202.5 foot-pounds per second. And for me, I will always take that unit. Sometimes people will not, they don't like that unit. Some things prefer horsepower. Horsepower is just one of those made up units that's not very helpful. You know, if ever somebody gives you horsepower, you have to convert it into foot-pounds per second to work with it. So it's not really my favorite thing. But so if you want to get from foot-pounds seconds to horsepowers, you divide by 550. So 11.277, 11.277 HP. I mean, the only nice thing about a horsepower is that, you know, one horse is an awful lot of foot-pounds per second. So it makes your numbers a lot smaller. So really we could say equals 11.3 HP, or we could say 6,200 foot-pounds per second. Okay, foot-pounds per second. Okay, whatever. Okay, and that's how we would solve this. Okay, I know I got a little sloppy at the end there. Sorry about that. But that's, I don't know, that's the fundamental, that's the idea. Okay, and to me, the key to all of this is really just being able to step back and can you get to this point, and more important than that, like, does it make sense? Like when you stare at it, you know, and you're thinking in terms of energy, like how does this work? Because even though it's very common, like the convention, and it's not completely the convention, but it's almost always to call this 0.1 and to call this 0.2. But really what you're doing is this is actually an in. So it's actually, we're accounting for the energy of this, and we're comparing that to the energy of this. So really what we're doing is this is an in, and this is an out of energy. And then all the friction is little losses of energy. So these are also little outs. This pump represents a major source of energy in. Okay. And so, I mean, that's really what's going on. Okay. And then obviously we've got more friction leaving right here. Okay. And so we tend to call this 0.1 and 0.2 because we're used to using Bernoulli. Every fluids class in the world probably teaches Bernoulli first and then teaches energy. And so, you know, anyway, so it's so interesting. It's so weird teaching. You guys are so quiet. Anyway, let's see if we can, let's see if I can find, another one that's much quicker. Let's see. Oh, yes, I love this problem. I don't know if we have time, but let's do this problem. Okay, so this is Same problem set, homework 12, number 5. Okay, I'm gonna go ahead and throw this away, clear my drawing. Okay, turbine is set up between 2 reservoirs. It's much easier for some reason. Pump problems show up a lot more than turbine problems. I don't know why. So we've got 2 reservoirs. I think I asked this one on a test. I can't remember. Anyway, so okay, we've got water up here or something. And then we've got okay, so it's something along those lines. Okay, turbine, head loss in the diagonal pipe. So head loss in this pipe, head loss due to friction is 5 V squared on 2G. The head loss in this pipe, in the vertical pipe, is 0.2 V squared on 2G. Okay, that must be a lot shorter. When the discharge is 0.7 cubic meters per second. How much power does the turbine remove from the water? So required W dot from water. Okay, and then B, what is the pressure at 1 and 2? Okay, P1 equals what? P2 equals what? And it tells you that this point right here is 1. This point right here is 2. Okay, we can assume there's no head losses in the pipes due to 1 and 2 due to bends, entrances, and exits. Okay, so basically there's no head loss here, 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 along here, here, and here. Okay, so all those circles that I drew, those are what's the word for them? Those are what we call minor losses, entrances, exits, bends, etc. And we're going to get to those, but we're just not there yet. So we're kind of like building this energy equation for you. And then so we're only going to deal with these head losses due to this kind of equation right here, as if this accounts for it all. Okay, so what we want to do here is, again, it's very similar to the last one, W dot. Okay, so what we want, so the W dot from the water. Okay, the equation is identical, so it's gamma HT Q. Okay, it's just like the last time. So what we need to find is HT. If we find HT, then we are good to go. Okay, the other thing, it tells you one other thing. It tells you the elevation here is 60 and the elevation here is 0 meters. Oh, and the pipe everywhere is 600 millimeters. Okay, the diameter is 0.6 meters. Okay, so again, I like this. We should have done this one first, maybe, because it's a little bit simpler. So let's go ahead and solve it. Here we got an aside over here. So the first thing I always know that I'm going to need is I'm going to need my velocities. So let's just go ahead and get that. Luckily, because the diameter here is the same through the whole problem and the Q is the same, we're going to have the exact same velocity everywhere. So let's go ahead and get that velocity equals Q over A. Okay, and this should by now be getting kind of like second nature, cubic meters per second. Okay, and the area is pi over 4 times that d squared, 0.6 meters squared. So that V equals, and of course I didn't give myself enough space, pi divided by 4 times 0.36, raise that to the -1 power, multiplied by 0.7, and we get 2.4757. 2.4757 meters per second. Okay, that's going to be useful for us. Okay, otherwise, we're just going to do the energy equation. And the easiest points here is going to be the points on the surface. So we'll go from 1 to 2. By the way, I will note that on the Bernoulli equation, it doesn't matter which point is point 1 and which one is point 2, because there's no energy loss. The two sides equal each other. But in this case, it does matter because the flow has to go from 1 to 2, okay? Or from the in to the out. Otherwise, you're going to break the law of conservation of energy. Okay, so here we go. Let's see, P1 over gamma plus V1 squared plus alpha C1 squared plus alpha V1 squared on 2G plus the pump equals P2 on gamma plus Z2 squared plus alpha V2 squared on 2G plus HT plus the H due head loss. All right, so let's just start analyzing points. P1 is, and again, what's really nice about these points by picking them on the surfaces is I don't have any velocities at either of them, okay? Because these are both tanks. And the nice thing about having no velocities in this case, one really nice thing, is that because we have no velocities, we don't have to deal with that alpha, okay? The pressures on both are 0 because they're atmospheric, okay? And then Z1, well, it has an elevation of 60, so we'll go ahead and use that. And I'll just say, see, so I don't lose this. I'm going to put it down here like this. It's 60 meters. Okay, I tend to lose these things. And then elevation 2, because it's, I mean, that's our datum. So this is the datum. All right. And let's see, HP, we don't have a pump. Okay. And HT, well, we have a turbine. And then this HL, we're going to split out into H due to minor losses, which is usually written as a lowercase l. And then this is going to be H sub F for the friction losses. Okay, so there is no, we're not doing the minor losses yet. And so we just got this HF. So I'm going to write this all out as, let's see here, 60 meters equals HT plus this HF. Well, it's got two parts to it, right? It's got an HF right here and an HF right here. So we're just going to add those two. I'm going to keep them separate because really they're in different pipes. I'll add them in a second because algebraically that's just 5.2 times V squared on 2G. But what's actually going on is you're losing 5 V squared on 2G in one pipe and 0.2 V squared on 2G on the other pipe. Okay, so basically all this energy, this potential energy in the stored fluid, we're taking out as much of it as we can with this turbine because we want that energy. We want to use it to power homes or whatever we want to do. But we don't get all of it. We can't remove all of it because we're going to lose some due to friction in the pipes. Okay, technically our turbine is not 100% efficient, but this problem didn't ask us about how much we'll actually get out of how much useful energy we're going to get out. It's just saying how much are we removing from the water. Okay, so we can go ahead and solve this. This is like straightforward. So I'll combine these two into 5.2 V squared on 2G. Let's just go ahead and get V squared. One of the things I like to do often is I just like to on the side get V squared on 2G because it's going to make my life a lot easier. So I'm just going to do this right now. I'm going to take that 2.4 blah 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 blah. It's already in my calculator, so I'm going to square it. I'm going to divide by 2G, so that's 19.62, and this equals 0.31240. 240, and that has units in meters. Okay, and that just makes my life easier. So I go down here and I can say, okay, well, 60 meters equals HT plus 5.2 times this. Okay, so take that, multiply times 5.2, and we get 1.6244. Oh, 5. Okay, not that it matters. Okay, that last one is just for fun. Okay, so that means our HT we can pull out. Well, maybe I can write it right here. HT equals let's see, minus that answer. 58.376. 58.376 meters. Okay, which means we can take an awful lot of energy out of this flow. And when I think conceptually, okay, again, potential energy is being converted into, well, some of it's being taken and the rest we're losing to friction. So one of the things to think about this as an engineer is that means we really want to limit these velocities because those velocities say a lot about how much energy we lose due to friction. And these, of course, are simplifications, but the the quote complications, or like the real world, the velocity hedge is really, really, really important. Okay, so anyway, so we're going to do this right here, this little bit, to solve it all the way. And I'll say, okay, well, W dot from water, okay, equals the gamma. Well, let's see, which system is this? That's 9810 newtons per meter cubed. HT, which is 58.376 meters, times Q, which is 0.7 meters cubed per second. Okay, and again, we want to check our units. Meters cubed are going to cancel. So I'm left with newtons times meters. That's joules per second. Joules per second is watts. So too many W's gets really annoying, but there's nothing really we can do about it here. So let's go ahead and multiply this, and we get 9810 times 58.37 times 0.7, and we get a massive number. This happens all the time with this number. 400,830, okay, watts. So usually in this case, we want to convert to kilowatts or megawatts. In this case, it looks like it's going to be 401 kilowatts. Okay. All right. So then the last bit of this, and this is, I'm gonna talk you through this real quick. I know we don't really have a lot of time, so if you need to go, by all means go. But I think this is kind of a really, really important point that a lot of my students miss. And so that's why I think I added this on. This was not part of the original question, to get P1 and P2. So I'm gonna go ahead and solve for both of those, because actually they're gonna be really easy. And so here's what I recommend. Well, I already labeled this as P1. So let's call this 0.3 and 0.4. Okay, so 0.3 and 0.4. Let me erase those so we can actually see. This is 3, this is 4. 3 and 4. Okay, now what makes these easy is that I can do both of these starting from 0.1. So I don't need to do the whole left-hand side of this equation again. Right, so I can go up here and I can say, okay, let's erase all this. Right, because I'm not going to 0.2 anymore. I'm going to 0.3. Which means, yes, I have to redo the right-hand side, but I don't have to redo the left-hand side. And the right-hand side is still 60 meters. Nothing's changed. Okay, so what's cool about this is now that we've done this, this is like fairly straightforward problem. Except of course, well, okay, anyway, we'll do it. So P2 on gamma plus P3 plus Z3 plus alpha V3 squared on 2G plus HT plus head loss due to friction. Excuse me, head loss, just head loss. Okay, so this is what we're looking for right here. Z3, well, that had to have been given in the problem. I didn't write it down, but it's certainly given. What does it say? Oh, elevation is 4.5. Elevation right along here. Elevation 4.5 meters. Okay, so this is going to be 4.5. Oh, let's do it in red. 4.5 meters. Okay, V3 on 2G. Well, that's this right here. Okay, I'm going to go ahead and assume this is turbulent because we don't have enough time. I think if you plug it in, you're going to find that it's turbulent. Okay, so we're going to assume 1.0. Between 1 and 3, there is no turbine. Okay, and that's kind of a key. Hold on, I'm going to close my door, start the storm. I'm a Rashi dog. I know. Wait for that door. Come on. All right, and then so that's kind of a key thing, is that that turbine is not between points 1 and 3, so it does not, we do not include it. Okay, and then the head loss. So the head loss between points 1 and 0.3. Well, we only have this head loss between 1 and 3. Okay, so this thing becomes 5 v squared on 2g. So I can write this as P3 on gamma. Well, on gamma in this case is 9810. Well, we're just going to leave it as gamma for now. Plus 4.5 meters. Plus this whole thing right here is this. So I'm going to have 0.31240 meters plus, and this is 5 times that. So I'm going to plug that into my calculator. 5 times 0.31240 is 1.562 meters. Okay. So again, this 60 meters, but we don't get all of that 60 meters because it doesn't go all the way down. And we're creating some velocity head and we're losing some due to friction. But the rest is stored in this pressure right here. Okay, so if I solve that equation, let's see here. 60 minus 4.5 minus 0.31240 minus 1.562. And then we're going to multiply that by 9810. And I'm going to get a pressure, P3 of 526,000. Okay, 070, and that's pascals, newtons per meter. Okay, so I'm going to go ahead and just leave it over here, just as a kind of reminder before we do the next step. 526 kPa. Okay, that's P3. Okay, now we're going to do it again, but I'm going to do it for the other location. I would like this. Can you just stay full screen? Okay. So we're going to do it for the other location. And again, I don't need, like, all this is going to change. Okay, let's see. So we got, this will be P4 over gamma. P4 over gamma. We're going to have the same Z. This will be Z4 is the same. We're going to have the same velocity. So all these things are going to be the same. This time we're going to have a turbine. But we already solved for the HT. Where was it? It's right here, right? I didn't write it down somewhere nice and clean, but it's right there. And we have the same head loss because we haven't added any more terms of head loss. All right, so this thing becomes, let's see, P4 over gamma. This is going to be P4 plus same elevation, same velocity head, 0.31240 meters, plus the HT, 58.376 meters, and then plus this 5 times V squared on 2G, which unfortunately I erased, but it's okay. What was it? 1.562. No. Okay. So again, you know, same idea. This 60 meters. We don't get all of it because we haven't gone all the way down, but now we're losing almost all of it to the turbine, which of course is the whole design of this system. We've got some velocity and we've got some head loss. Not all the head loss, but most of it, right? So the only difference between 4 and 2, is there's just a little bit of head loss, a little bit of energy loss along these walls, and we lose some elevation. So let's go ahead and let's see. So we'll just plug this into the calculator because there's one last point to be made. 60 minus 4.5 minus 58.376. Did I get everything? Minus 0.31240 minus 1.5620 equals. Oh wait, and then we need to multiply that by 9810. Okay, so unless I made a calculator error, which is certainly possible, negative 46,601. And that's what is that? What are the units on that? Okay, that's sorry, that's newtons per meter squared or pascals. So P4 equals 46.6 kPa negative. Okay, and again, it's a tendency. There's a tendency to, like, when we see the negative, to go, I screwed up. And I don't think that that's a bad inclination. Is like you get a number, you should always stop and think about what it means. But in this case, we've got a negative pressure right here. And what's interesting really is that in this case, all of the energy that was removed by the turbine is pressure energy. And it actually brought us to a pressure that is below atmospheric. And you might say, well, why is it below atmospheric right there? And the answer is it's easier to think about from point 2. If I were to go from point 2 to point 4, let's imagine it's hydrostatic. Okay, well, the first thing that's going to happen is, okay, so we've got 3 things. P, we're going to ignore the head loss. P, V, and Z. Okay, so this is from Bernoulli, right? You've got these 3 quantities. And if there's no energy loss, they all have to add up to, like, the heads all have to add up to 0, right? So as I move upward in a fluid, if we think back to hydrostatics, okay, the pressure has to go down because I'm moving upward in a fluid as I go from 2 to 4. Okay, the pressure has to go down due to hydrostatics. The velocity as I go from 1 to 2. Okay, yeah. Okay, wait, hold on. This is not right. Sorry. Ignore what I just said. Okay, as I go from 2 to 4, Z increases. Okay, as I go from 2 to 4, 2 has no velocity, 4 has a velocity, so the velocity increases. So the only way I can make up for that is to have a tremendous pressure drop because the velocity, because both of these go up. So this has to accommodate both of those. The pressure has to go down. The pressure at the surface here was 0, so it has to be negative at that point. Okay, the only thing counteracting that is the fact that we're losing energy as we go from here to here. Okay, due to, this head loss right here. So it actually counteracts it. We need a little bit of pressure here in order to drive the flow from 4 and overcome that head loss. But that's just an aside. In a perfect world, if there were no energy loss, this pressure has to be lower than this pressure. Okay, it's the same as the straw problem. You have to create a lower pressure above in order to, except in that case, we're using Bernoulli and not energy. So anyway, any questions? I know that's kind of I don't know. To me, I love this question, but I could on an exam just say like, well, what's the pressure right here? Now I'd have to give you the elevation, but you should be able to figure it out. And if you go from point 2 to here, then you include the turbine, right? And if you go from this point to here, you don't include the turbine. It just depends on how you draw your energy equation. And what you want to do is make it as easy as possible. So if I were to ask for this pressure right here, I would say don't include the turbine and go from this point to this point, because that's going to make your life easier, right? And plus, if you made a mistake, an algebraic error or something calculating the turbine earlier, it doesn't compound on you. I don't double count for errors, but down the road, it's just kind of a good habit to get into because I don't know how other people grade. So anyway, questions? Or none, either way. It is a beautiful day for a nap. My Lord, it's a beautiful day for a nap. It's about as dark outside as it is in Paul's black background.
Yeah, I need one.
We all need a nice nap every now and then.
Mm-hmm.
So anyway, you guys cool? Any questions?
I'm good.
It's something that, like, again, once you play with it a little bit, you'll see what you're confused with or if there's any confusion. So play with it. We're going to be working on this till the end of the semester. So just, make sure it makes sense. Okay. Well, then I'll see you guys. Thanks for everything. Thanks for being a good audience.
Thank you.
All right, guys. See ya. Let's see here. Recording, stop.